Hello again. This is Zach with Mechanical Engineering 3260, System Dynamics and Vibrations. I'm going to be doing homework problem 2.4. And we need to find the equations of motion of this system here. And for fun, we're going to use energy methods rather than force diagrams. So to do that, and we can do that because this is a conservative system. We have static friction. It's not going to take any energy out of our system. So we can just sum all the possible energies of all the objects in the system, set it equal to 0, and then find our equation of motion from that. So, as you hopefully recall, the energy for a spring is 1/2 kx squared, 1/2 spring constant times the displacement of the spring squared, and the energy of any moving mass, any translating mass, is 1/2 mv squared. This is also known as 1/2 mx dot squared. And then we also have the energy of a rotating object, a rotating body, is 1/2 I omega squared. For us, the inertia is 1/2 mr squared, so we have 1/2 times 1/2 mr squared. And then omega squared is the same thing as theta dot squared. And here you can see x and theta defined. So we'll sum all the energies, set it equal to 0, and find our equations of motion. So K1 will have an energy, 1/2 K1, and x is the displacement we use for the stretching and compressing of those springs, x2 squared. K2 will have an energy, sum that energy, 1/2 K2 x squared. We will have an energy for the translation of this body, 1/2 mx dot squared, and then obviously an energy for the rotation of this body, and then these are all the energies, and at any given time the summation of all the energy is going to be 0, because any energy expended by one thing is going to be put into another part of the system. And there's no heat dissipation in this conservative system. Alright, the only other thing we need to know to solve this is because of the no slip condition, we have x equals r theta, which also means x dot equals r theta dot, and that's all we're going to need. So we'll simplify this, rearrange it a little bit, and actually take the derivative in order to get x double dot into the equation, which we want. At the end of the day, we do want x double dot, mx double dot in our equation. So everything is multiplied by 1/2. We can get rid of that. Multiply through by 2, and it'll just disappear. Then we have both K1 and K2 multiplying x squared. Then we have mx dot squared plus, and we're getting rid of one of the 1/2, so we still have one around. And then you can see we have r squared theta dot squared. Comparing that to r theta equals x dot, this term right here is just x dot squared. So we have plus 1/2 m x dot squared, still all equally setting it all equal to 0 still. Simplify a little more, why not? K1 plus, oh, that's K2. K2 x squared plus we have 3/2 m x dot squared equals 0. Alright, so we need to get x double dot into here, so we're going to take d by dt out of this whole thing. So we will get k1 plus k2 times the derivative with respect to x, and then the derivative with respect to t. This is by chain rule, plus take the derivative with respect to x dot multiplied by the derivative of x with respect to t. This is 0. Alright, once again, we can get rid of some 2's by dividing everything by 2. And then I'm going to pull the x dot out front, since it appears in both terms in our equation. Okie dokie. So there's two solutions here. One solution is the trivial solution, which is x dot equals 0. Static at rest, 0 energy equals 0. That's the trivial solution. And then the other solution is our equation of motion, which is just basically repeating here, just rewriting the same thing. Bam, equation of motion. With skipping steps, I mean, a system like this you can hash out in like maybe a minute. But there it is. Good deal. All right. That was homework 2.4.